Press play. Is your screen not showing? You need to change yourself. Hello everyone, I'm Katie Contos and welcome to today's webinar, which is hosted by the National Renewable Energy Laboratory. Today's webinar is focused on the Nuclear Innovation Clean Energy Future Technology Overview, Integrated Nuclear Renewable Energy Systems. Before we begin, I'll quickly go over some of the webinar features. For audio, you have two options. You may either listen through your computer or over the telephone. If you choose to listen through your computer, please select the mic and speakers option in the audio pane. If you choose to dial in by phone, please select the telephone option, and a box on the right side will display the telephone number and audio pin you should use to dial in. If anyone's having any technical difficulties with the webinar, you may contact the GoToWebinars help desk at 888-259-3826 for assistance. If you'd like to ask a question, we ask that you use the questions pane where you may type it in at any time. Also, the recording of today's presentation will be added to the YouTube channel, and the link is provided at the bottom of this slide. Today's webinar agenda is centered around the presentations from our expert panelists on the technology overview, integrated nuclear renewable energy systems. Before we launch into the presentations, I'll provide a quick introduction of today's panelists. And then following the panelist presentation, we'll have a question and answer session where the panelists will address questions submitted by the audience. First up today, we have Sherry Bernhoff, who is the Senior Program Manager at Electric Power Research Institute. Following Sherry, we'll hear from Dr. Shannon Bragg-Sitton. Shannon is a Manager of Systems Integration, Nuclear Systems Design and Analysis Division, Nuclear Science and Technology Director at Idaho National Laboratory, and the Program Lead at the U.S. Department of Energy Office of Nuclear Energy Program on Nuclear Renewable Hybrids Energy Systems. Following Shannon, we'll hear from Mark Ruth, who's a Project Lead and Engineer in the Strategic Energy Analysis Center at the National Renewable Energy Laboratory. And our final speaker today is Dr. Gina Shaddy, who is the Energy Program Director at Canadian Nuclear Laboratory. And with those brief introductions, I'd like to welcome Shannon to the webinar. Shannon?
Thank you very much, Katie. Next slide, please. Before we begin in talking about the technology that we are working on, I want to begin by giving an overview of what the Nuclear Innovation Clean Energy Future Initiative is. The reasons behind establishing this initiative under the Clean Energy Ministerial is to begin recognizing that nuclear energy is a very important contributor to global clean energy supply, and it will continue to play a role in meeting future clean energy goals. However, in many of these clean energy fora, nuclear often doesn't come to the table. Therefore, it was recognized that there was a gap, and we needed to establish this dialogue on the role that nuclear can play alongside other forms of clean energy. Looking at the initiative itself, it has four primary focus areas. First, on technology evaluations associated with coordinated energy systems, innovative technologies for these systems, energy storage, and various energy uses that can be coupled with nuclear. Second, we look at engaging policymakers and stakeholders regarding the energy choices for the future. Third, a focus on economics, including valuation, market structure, and the ability to finance such energy systems that we were talking about. And finally, working on communicating nuclear energy's role in clean integrated energy systems. Next slide, please. Before we get started within the detailed slides today, I want to just put out these three areas, what it is that we would like you all to get out of this webinar. The technology options that we are presenting today are designed to demonstrate that, number one, flexibility and resilience are necessary attributes of our future energy systems. Number two, that nuclear energy can be applied beyond baseload electricity generation, where it commonly is applied today, in order to meet a broader set of energy needs across various energy sectors, including industry and transportation as well. And finally, nuclear plants can be coordinated with variable renewable generators in order to maximize penetration of clean energy in meeting the energy needs that we have across all energy use sectors. With that, I'd like to go to the next slide and welcome my colleague, Ms. Sherry Bernhoff from the Electric Power Research Institute. Sherry?
Oh, thank you, Shannon. The next slide, please. So Shannon teed up that there are some attributes of nuclear power that are important. I'd just like to emphasize some of those. Flexible operations has occurred, and flexible operations is basically defined as non-base load operations. This has been an important element of operations in France and Germany for a long time. Typically, though, the plants in the US, throughout the EU, and other areas of the world have been base load operated plants. That means that they sit at 100% operations. But this is changing. And the big drivers that are causing this change is, of course, the increase in renewable penetration. We're seeing areas of grid congestion, and we're seeing areas of negative pricing. And we fully expect that this variability that's occurring on the grid and driving the need for flexible operations is going to continue to increase. Now, in about 2014, EPRI started looking at some research areas in there and formed a technical advisory committee. And the group has been pulled together. It's a very global group. We're proactively looking at some of the research needs to understand the impacts on the plant so they can continue to be safe and reliable as they operate flexibly, looking at management strategies. We've pulled in a large group of stakeholders, including, Shannon's been one of our key stakeholders, and we share operating experience to promote safe operations with the recognition of flexible operations. Next slide, please. So here's an example. This is very typical of what is occurring right now in the Southwest of the United States. But this would be any market where you're going to see a lot of solar operation. I think a lot of you are familiar with the duck belly curve. What it shows is that during the middle of the day when you have high solar and maybe lower demand, you need to curtail dispatchable generation. And we expect that to continue with more solar growth in many of these markets, to the point where it'll start needing to curtail and is starting to cause curtailment of some of the nuclear power plants. But they're looking at this curve in aggregate. There's two things that you want to keep in mind. One is look at the depth or how low some of the plants may need to start curtailing their generation. And then a second area that we need to be looking ahead at how we're going to manage for the overall grid system is that ramp rate that comes in the late afternoon, evening hours as the solar is no longer available and there is a need to start providing generation for the peak period that happens later in the day. We also, not shown today, but there's also several plants that are in upper Midwest, nuclear power plants in the upper Midwest that are cycling due to wind generation. And there's also a plant in the upper Northwest that is cycling due to high hydro generation, particularly in the spring months. Next slide, please. One question we get is, how can the nuclear power plants operate flexibly? To study that question, we looked at three different scenarios. One is a pre-planned case where they can respond to what we call some of these high renewable responses. We do have quite a number of plants in the US and globally that are operating kind of this pre-planned band, being able to maneuver their plant between 100 to a low of 80 to 70% and then back up to 100% in this day duration to be able to respond to wind and solar generation. There are some plants that have a pre-planned window where they'll go to a reduced power for an extended period of time. That's particularly seasonal in the spring and the fall. Like I said, that's occurring right now in the upper Midwest in the US, and it's a mode that's being looked at by some of the newcomers like UAE in the winter and China also in the winter months are looking at these pre-planned evolutions at a reduced power. Then we're looking ahead also as that duck belly curve or wind causes increased variability on the grid. Do we need to start looking at scenarios where you have to go lower in power or be able to maneuver the plants more rapidly? So we are starting some of the case studies on that. What I can say today is that for the first two cases, this is being safely done with some minor changes to the plant and their operating procedures and their training to start moving into what we call the more extreme case. That last scenario that is going to require some modifications to the plant and the plant licensing design. But what I want you to walk out of this today is that nuclear power plants are flexible, and they are able to integrate with the grid to support the situation with some of the increasing grid variability. Next slide, please. In looking at the different impacts on the plant, from an EPRI standpoint, we put together a large team of subject matter experts. And these are the different areas that we started the research on in 2015. You can see them looking at the fuel integrity, the chemistry, radiological safety, the flow accelerated corrosion, the various balance of plant impacts, and the impacts that could happen on the primary side long term with flexing your plants. What we have found through the research and the gathering of operating experience is that flexible operations is successfully being implemented right now at a number of plants, and there are impacts, there are some measurable impacts, but they are being safely managed with proper operations and training. Next slide, please. So what we want to do is we also want to be looking ahead. Flexible operations is a global issue, as I said before, primarily with the driver of the increase in the renewables, but also with changing consumer behaviors, distributed energy, microgrids. There are a number of drivers that are going to continue the need for flexible operations. And looking at the other side with the grid, the ability to manage the variability on the grid to keep the resiliency of the grid up. So we do need to start looking at a couple of things. One is, what is the ability of the existing plants and the new plants for faster or deeper maneuvering? We're coordinating some of that with like an accident tolerant fuel project. But we also need to start looking at some of the other things that were being asked. What long-term are some of the grid services that are being provided by the nuclear power plants, the synchronous generation that's on the grid too? And how does that need to be factored into the whole energy picture to ensure that long-term you have a good balance on the grid between the synchronous generation that's provided by a large baseload unit like a nuclear power plant and allowing an emerging renewables market and keep the grid safe and stable, or resilient is the term that's being used. And then also, how can we look at the economics of the situation? This is what Shannon's going to get into a lot more, and that is, can we take some of this surplus energy during periods of low demand and high capacity on the grid and find other uses for it to help improve the overall economics and the stability of the grid? Next slide, please. So with that, as I transition to Shannon and her presentation, I just want to emphasize when I talk about, the grid and the resiliency of the grid, these are just some of the key attributes that, today we need to make sure as we go into the future scenarios, looking at flexibility and resiliency, that we also allow the market to be able to ensure that these services are also still provided on the grid. And that's other areas of research that we're looking at as well. With that, I will turn that over to Shannon.
Hello, Shannon. This is Katie. I think you might still be on mute. Give us 1 second while we figure out some technical issues with Shannon.
Figure it out.
My apologies, everyone. It seems that we seem to be having some technical issues with Shannon.
Katie, my connection just came back up. It just went out for a moment for some. So I'm back.
Wonderful, wonderful. Well, welcome to the webinar again, and why don't you go ahead and get started?
Great, thank you so much, and I do apologize for the gap. So, not sure, you should be looking at the first slide in mine, the generating energy system flexibility. I still see the last of Sherry's slides. Oh, there we go. I've got it now. So Sherry talked about our nuclear plants can certainly operate flexibly from a technical standpoint, and from a safety standpoint, this is a good option as well. However, we are looking at other ways in which we can generate energy system flexibility such that our nuclear plants can continue to provide the reliable baseload services that they do right now to the grid, and maintain a very strong economic performance by providing excess electricity and or heat to other applications. Our overall goal is to provide a sustainable, balanced energy portfolio that provides us with reliable, resilient electricity at stable and affordable prices. So here we are looking at the proposed solution that offers an integrated solution or coordinated solution, whereby we utilize energy generation from nuclear plants, whether those be the current fleet of light water reactors, large-scale light water reactors, or future small modular reactors and higher temperature advanced reactors, in coordination with the other generators on the grid, wind, solar, as well as fossil energy, to meet those electricity needs, as well as to begin penetrating other areas of energy use in industry, production of things such as hydrogen that can be used in fuel cell vehicles or in other offtake industries, production of clean water, or even in new chemical processes that might be designed to take advantage of the heat and electricity from these systems as well. In this way, we are able to maximize flexibility and economic performance of these plants while still ensuring reliability and resilience. Next slide, please. So here I want to provide an overview of the scope of the program that we are conducting under the DOE Office of Nuclear Energy, and we do coordinate this program with the Renewable Energy Lab and the Office of Energy Efficiency and Renewable Energy, also within the Department of Energy in the United States. When we look across the DOE-NE program, this breaks down into two major areas. First, in the area of modeling and simulation, we have been focused on the development of advanced tools and conducting the associated analyses that allow us to assess the technical and economic viability of these types of integrated systems, as well as to optimize the system design and the real-time dispatch of energy based on the current demand from the grid, as well as renewable energy input in that particular region. So I'll talk a little bit about two pilot case studies that we are doing this year that are focused on specific operating nuclear plants in the United States and working with utility partners to do those studies. In the second area, we're focused on demonstration of these integrated systems. In this case, we are developing a laboratory to conduct electrically heated or non-nuclear testing of integrated energy systems that emulates the heat that would come from a reactor, from a pressurized water reactor initially, in order to demonstrate hardware interfaces, to demonstrate complex control systems as we maneuver energy from one user to the next, to demonstrate the dynamic operation of these systems. So we're currently working on the design and building components of a thermal energy distribution system that will connect to a pressurized water reactor emulation loop, initially connected to hydrogen electrolysis. And the image you see in the lower right is included here to represent some of our collaborations and why we are focusing on hydrogen here. We are collaborating within multiple offices of the Department of Energy, specifically with energy efficiency and renewable energy, looking at the production of hydrogen via numerous energy generation sources, one of which can be nuclear, and we are working to demonstrate that in our laboratory via high temperature steam electrolysis. We're also working with industry, with a number of utilities via a utility advisory committee that I have established in collaboration with EPRI, with Sherry, and also working with a number of end users to understand how we might efficiently use the energy from these nuclear plants. Internationally, we're engaged, of course, with the Clean Energy Ministerial via this initiative, as well as other countries directly that are interested in these integrated energy system options. Next slide, please. Here I just show an example of how we are approaching the optimization of these systems. Without going into too much detail, and you'll be able to look at these in more detail on the slides later, the optimization approach that we are using is multifaceted. First, we look at optimal system sizing, so the component sizes within the system, and then overlap that with optimization of dispatch of the energy in real time based on net demand within a particular location. So the example that you see here and how we are using this optimization code, and we're using an in-house developed code at Idaho National Laboratories, is called Reactor Analysis and Virtual Control Environment. This tool wraps around very detailed dynamic models of the system that we are modeling in order to allow researchers to understand and manage the probabilistic nature of these complex systems via their numerical representation. So Raven is used to wrap around a code called Modelica, where we've developed these detailed dynamic models. And the initial study that we've done, and the example shown here, includes a reactor system. The industrial process here is hydrogen generation. We also include an energy storage component. In this case, we're beginning with battery storage, and a gas turbine as well to provide additional peaking power when needed in order to optimize the system performance should we want to direct more toward hydrogen production at different times. So when we do these optimizations, we are looking at varying the system capacities initially to design our system in the best way we can. And we use real data from the particular region. In this case, we are looking at wind penetration in the region. So there's an existing wind farm that we have assumed in this region. And we are also developing those tools to do this with solar as well. If you go to the next slide, what you'll see is an example of the performance of a system that utilizes these different components. So in this case, we've run an optimization for component sizing. And what I show here in the plot is how the energy is being maneuvered in the system in real time. So this is using a net demand signature from a particular balancing area, a particular area within the grid. And what you can see is that we are maneuvering energy from the nuclear plant between the balance of plants, so producing electricity, and production of hydrogen. We set a number of constraints within the system on how rapidly things can be maneuvered, minimum operating ranges. For instance, the hydrogen plant is never shut down to zero, but has a minimum operating range in that. And we're maneuvering the energy around based on the net demand such that we always meet the electricity demand in the region. We've applied penalties for missing that demand or for overproducing electricity, so we can begin to understand how the systems might maneuver energy in real time in order to maintain economic performance. So we go to the next slide, you'll see how we are now beginning to apply this tool set in a couple of different case studies. So the examples on the previous two slides were purely a fictional example of what we might look at. And now we are using that tool first to study the potential integration of an existing nuclear plant with solar generation, specifically solar photovoltaic generation in the southwest region of the United States, specifically in Arizona, for the production of clean water using a brackish water source in that region. So here we are looking at the electrical integration of the existing nuclear generation in that region with a desalination process, specifically reverse osmosis, but we may also look into some other technologies as well. That is in collaboration with Arizona Public Service, which is the operating owner of Palo Verde Generating Station, as well as EPRI. The results of this study should be available in the September timeframe, looking at the economic performance of these systems. In the second case, we are looking at the Midwest region, which Sherry mentioned is currently being impacted by increasing generation from wind. So the variability we see in this region is very different than what we see in the Southwest region of the US. In this case, we are looking at repurposing or retrofitting an existing light water reactor in that region to support an industrial application in addition to electricity production. Initially, we will focus on hydrogen generation using high temperature electrolysis and looking at the economic scenarios associated with using that hydrogen in a number of offtake industries, for instance, steelmaking or ammonia production, as well as fuel cell vehicles. And this is in collaboration with multiple industry partners led by Exelon and with consultation from EPRI as well. On the map on the right, you simply see a highlight of those organizations and companies that are involved in the Utility Advisory Committee that are helping to guide the research that we are doing at the National Laboratories. Next slide. In addition, as I mentioned previously, we are working on the experimental demonstration of integrated systems. This is a rough configuration for what we are working on in the Dynamic Energy Transport and Integration Laboratory, where the objective of this laboratory is to demonstrate the simultaneous, coordinated, and controlled and efficient use of multiple energy generation sources for multiple energy uses. So as you can see, we have representation and hardware components for renewable energy generation, including both wind and solar. We've got representation of electric batteries, and we are now building out the bottom portion of this figure where we have completed the design and are ready to build a loop that emulates a reactor, the thermal energy input from a pressurized water reactor. In the middle there, you see the thermal energy distribution system, which will also include a thermal energy storage component. And then we have steam user processes. Initially, that will be a high temperature electrolysis system. This is all in coordination with real-time digital simulation of the power systems that would be entailed in a microgrid configuration, and allows us to look at how this interacts with the grid and how we maneuver this energy around through these various users. Next slide, please. What you see here is just a snapshot of what the lab looked like about a month ago. So we have a lot of these hardware components already in. Additional representation here is the battery charging station. So we do a lot of testing of electric vehicle battery charging options. And this gives us a variable electric load that we can also use within this integrated system test facility. And finally, my last slide, I just want to highlight the fact, if you go to the next slide, please, that right now our nuclear plants are primarily used just for electricity. There are some additional applications in other countries that are being used, but in the United States, it's purely for electricity. What this program is about is looking at how we might reimagine the use of nuclear energy in order to maximize our energy utilization through novel systems integration and process design. So again, using that heat and electricity in new ways to impact multiple areas of our energy sector. At this point, I'd like to hand it over to Mr. Mark Ruth at the National Renewable Energy Laboratory to talk about some of the economics associated with these systems.
Thank you, Shannon. As Shannon mentioned, I am at the National Renewable Energy Laboratory, which is the U.S. Department of Energy's Office of Energy Efficiency and Renewable Energy's primary laboratory. As in that role, I am leading the effort, or have led the effort, on the EERE side of the partnership between the Office of Nuclear Energy and the Office of Energy Efficiency and Renewable Energy in this area. I'm going to present a few of our analyses and the analytical results of what we call the nuclear renewable hybrid energy systems, which are the systems that Shannon described where thermal and or electrical energy from nuclear plants is used for industrial processes. We did 4 specific industrial processes. We performed analyses on 4 specific industrial processes here. And I want to note that all of them we looked at what we call greenfield opportunities. In other words, these are building and constructing of as designed plants for these purposes, as opposed to or as compared to some of the analyses that Shannon described, where they're looking at existing plants. We're just looking at it in a slightly different way. The four different nuclear renewable hybrid energy systems that we analyzed are shown here on this slide, as are for each one of them the reports reporting their results. I'll show some results in this very short presentation, but obviously in the interest of time, I won't be able to get to very many of them. You feel free to download any of those reports and find more information on any of those. So the top two are, well, the process in the upper left is focused on producing liquid transportation fuels. In other words, converting natural gas to a liquid fuel using a lot of thermal energy generated by a nuclear reactor, while at the same time allowing that nuclear reactor to produce electricity for the grid in coupling with a wind power plant. The one on the upper right is very similar to the Arizona design that Shannon mentioned, which is looking at using a reverse osmosis desalination option with a nuclear power plant and PV photovoltaic electricity generation to support both the grid and then to produce desalinated water or potable water. That differs, one of the key ways that differs from the one in the upper left is that the one in the upper right only has an electrical coupling between the nuclear power plant and the industrial process, whereas the liquid transportation fuel option on the upper left has both a thermal coupling and an electrical coupling. In other words, that industrial process uses both heat and electricity, as opposed to just electricity in the upper right. As we moved through our analysis, we added another option, which just looked at the use of thermal energy, because we were finding that the use of thermal energy is very valuable, that the thermally generated energy from a nuclear plant is very valuable. However, because the nuclear reactor, a nuclear reactor just producing thermal energy and electricity and following the grid, as Shannon described, the net load on the grid, would not produce thermal energy in a way that is constant as most industrial processes need it. We needed a thermal storage option and an electric boiler option to be able to produce that constant thermal product. And then on the bottom right, we analyzed two different options for producing of hydrogen. One option is high temperature electrolysis, which has both the thermal and the electrical coupling, and the one on the bottom right, and the other is a low temperature electrolysis on the right side, which has just exclusively an electrical coupling to be able to produce hydrogen. In those cases, not only could electricity, the electrolyzers could use not just electricity produced by the nuclear power plant and or the wind plant, but also the grid itself, purchase power from the grid. The process that we used, or the questions that we were asking within the analysis is the nuclear renewable hybrid energy system more profitable than uncoupled configurations and then competing technologies? The real question we were asking is, where does this technology make sense as opposed to other technologies from the viewpoint of the owner in analysis question number one? And in number two, it's does the flexibility help support the resource adequacy of the power grid, and does it increase profitability? The first part of that question is asking, how might nuclear renewable hybrid energy systems support the grid and what's the value to the grid? And then does that impact the profitability of the plant? So the process that we used is somewhat similar to the one that Shannon described in terms of their modeling optimization. However, we looked at a lot more of the environmental issues. In other words, following our process, we were able to look at different grid generation mixes, different prices, different external factors on the nuclear renewable system. And to be able to do that, we developed a grid, or we analyzed the grid in each one of those two locations that we looked at, Texas and Arizona, that had very high penetrations of wind or solar photovoltaic generation, depending on the location. That grid then gave us a very highly variable grid, one that was even more extreme than in the duck curve that Sherry described. And then within that grid, we used a security constrained production cost modeling option to estimate the cost of producing electricity during each hour of the year. So during hours where there's a very high load and very limited amount of renewable generation, there would be very high costs due to the need of running peaking natural gas plants, natural gas combined cycles, and other plants on that grid. We then added a capacity payment, which added an incentive to be able to provide electricity during the high need hours, the 50 hours during the year with the highest load, and then having that information as well as the capital and operating costs, we did a dual optimization, somewhat similar to what Shannon described, where we optimized what is the optimal configuration, in other words, which subcomponents are necessary, and then how would they be operated, or the dispatch between them to be able to perform our analysis. I'm only going to show results on one of the numerous configurations that we considered. This is the one that was at the left side of the lower right one several slides ago, and it's a nuclear renewable hybrid energy system with high temperature electrolysis. In this case, we were looking at this couple of both a thermal and electrical coupling of the nuclear reactor and the high temperature electrolyzer to be able to produce hydrogen. And electricity could also be produced by either the wind plant and or the power grid, as well as the nuclear reactor, to be able to produce the hydrogen. And we ran it through our analysis process. In this slide, we start to show some of our results. So what we did is we varied, as I mentioned, we varied the external factors. So we had this highly variable electricity price over 8,760 hours of the year, and then we added a multiplier to it. You can see the multiplier on the y-axis of this figure on the left. So we used at 1, it was just the numbers that we got from the production cost model. At 2, we doubled those costs. So any electricity that had a 0 cost was still 0, but if the electricity cost was, say, $70 per megawatt hour, it would then be $140 per megawatt hour for that given hour. On the x-axis, we varied the selling price of hydrogen. So the cost competitive selling price of hydrogen is shown by that black dot, which is about $1.30 per kilogram. That's produced from steam methane reforming in our case. And then we varied that all the way down to essentially 0 value and all the way up to $10 per kilogram selling price of hydrogen. We then ran our optimization, as I described, for both the mixture of the components and the dispatch within it. And you can see where it met our hurdle rate of 10% after tax, and that is everywhere where there is a dot. Where the different color dots tell you which configurations met the hurdle rate and were most cost competitive. I don't show the other cost competitive ones that were not as complete of a configuration. So the upper right is the full nuclear renewable hybrid energy system showed by the pink dots, and that includes the nuclear reactor, the thermal power cycle, the wind renewable electricity generation, and the high temperature electrolysis. As you can see, at an electricity price multiplier, you would include those electricity generators above 1. At the upper left, you start to see that you would not produce hydrogen generation. So the orange dots show that there's just a nuclear reactor, thermal power cycle, and renewable electricity generation or wind generation, which shows that there you're exclusively trying to produce electricity and there's no value to produce hydrogen. It's because it's too far to the left, that kind of diagonal line that moves from the purple dots to the yellow dots after the pink dots shows where the break-off is. On the left side, you want to produce, or the left side, you only want to produce electricity. On the right side, you want to produce hydrogen as well. Going up to down, there's also a break point where in kind of the light blue dots in the middle, there's the desire to produce hydrogen, but not to produce any electricity, or the optimal configuration is to produce hydrogen, but not to produce electricity from the nuclear reactor. So in other words, the nuclear reactor produces heat, and then the renewable energy and purchased electricity produces hydrogen because that's the most profitable configuration. In the yellow, the electricity price is so low that there you just want the nuclear reactor to produce heat, and then you want to purchase electricity. And then on the purple dots on the lower left, you start hitting a point where there is some value to compete in the electricity market as well. So that gives you a list of the configurations. Moving down to the next slide, you start to see how much electricity is purchased. As I mentioned, in the lower part, the optimal configuration purchases as much electricity as is possible because the electricity price is so low, whereas the amount of purchasing as you move up to the right is much lower. So you produce, or you use self-generated electricity either from the nuclear reactor and thermal power cycle or from the wind cycle. And as you move further up, you use more and more from the nuclear reactor itself. This figure shows how much capacity is provided to or this set of figures shows how much electricity is provided based on different capacity payments. The three different figures match the figures we had before, but instead of showing the configuration or the utilization of electricity, they show the amount of capacity awarded. So the dark blue shows a full capacity payment. In other words, the nuclear renewable hybrid energy system is taking advantage of as much capacity payment as is possible at three different levels, hence the three figures. With the lowest level of capacity payment of $50 per kilowatt year on the left, $100 per kilowatt year in the middle, $150 per kilowatt year on the right. And the higher the capacity payment incentivizes more price combinations to be able to meet the profitability requirement and to be able to design for the full nuclear renewable hybrid energy system. The base case that we used was the $100 per kilowatt hour, and hence we ended up in a capacity payment point where we wanted that the full nuclear renewable hybrid energy system as much as possible above an electricity price multiplier of 1. As that payment goes up, we would want that fully configurable nuclear renewable hybrid energy system more often, as shown on the right. In conclusion, what we found was that hybridization and flexibility improves the profitability. However, it does not make sense for an owner to design and operate hybrid systems as the one are proposed unless there is sufficient incentives from the energy system that pays for those services. One of those incentives is a capacity payment, and when that's large enough, then you'd want the full configuration and want to support the grid during the key hours. However, that still does not happen unless there's a high enough value for the industrial product and for the electrical energy. With that, I'd like to turn over the presentation to Dr. Gina Strati at the Chalk River Laboratories in Canada to be able to present some of the work that they're doing in terms of implementing some of these designs.
Thank you, Mark. I think I'm off mute. Great. Thank you very much for the opportunity to talk to you a little bit about some of the clean energy research that we're engaging in at CNL. My presentation is at a bit of a high level because I want to give you a flavor of the type of work that we're doing and some exciting things that we're planning to do in the future. Next slide, please. This slide is really for those of you who are not familiar with the Chalk River Laboratories and Canadian Nuclear Labs. So we have a large site, 9,100 acres and about 200 acres of lab complex, nestled on the edge of the Ottawa River. And we have 17 nuclear facilities engaged in a variety of different research. In addition to clean energy research, we're also engaged in health and environment nuclear research as well. Next slide, please. So when I think about integrated nuclear and renewable energy, I think we went one slide too many. When I think of integrated nuclear and renewable energy, I really view this as a very holistic problem where all of these different types of technologies, these clean energy technologies, nuclear and renewables, work together synergistically to provide enough power for us to live the way that we want to live and use the new technologies that enter the market on a regular basis. So this would include the wind power, the solar power, nuclear power, and hydrogen production to power our vehicles, our homes, and our industries. So really it is, like the other panelists have talked about, a real synergistic problem that we need to focus on together and not separately. So really, nuclear as a standalone isn't enough, I think, to cover all of the needs globally for clean, reliable energy. Next slide, please. We really are, I think, experiencing an environment for success in clean energy options. There are a lot of domestic and international initiatives that are really setting the stage positively for us to be able to achieve a synergistic clean energy solution for the world's energy needs. And it goes beyond the SEM and NICE initiatives and other agreements. In Canada alone, we've targeted doubling our research development money and for demonstrating clean energy technologies. There is a lot of interest provincially and nationally in deploying small modular reactors and increasing low carbon energy solutions for remote communities and industries. And just recently, NRCan has supported an industry-led SMR roadmap that encourages alignment of the Canadian SMR industry and answers the question, what does that look like for Canada, and how does a small modular reactor fit into our clean energy needs? Next slide, please. Part of our clean energy program, we focus on a number of different areas for our current existing fleet, as well as new and advanced reactors. I've highlighted two of these areas that I think are really important to advance future clean energy integrated technologies, and that is our goal to demonstrate the commercial viability of a small modular reactor by 2026, and our goals to decarbonize the transport sector and remote communities in Canada through our hydrogen research. So those two areas in particular are really critical to being able to demonstrate these integrated solutions for our energy needs. Next slide, please. The small modular reactors are very talked about today. It is a technology, the small reactors and advanced reactor technologies are really could be very transformational in the way that we approach energy generation and location of small reactors within communities that are otherwise isolated from large electrical grids. So we really view the small reactors as an enabling element of an integrated clean energy solution. Next slide, please. Part of our goals to move the deployment of SMRs in Canada forward, we are really focused on having the Chalk River Laboratories and other CNL managed sites as demonstration sites for a small modular reactor. We've looked at our different sites and have identified more than half a dozen areas that could be conducive to building a demonstration project for SMRs. Last year, we solicited input from the global community on what an SMR industry in Canada would look like, and specifically on the need for a demonstration of this new technology in Canada. And there was a really positive response to that request. And so this year, we've moved that yardstick a little bit forward and have issued an invitation in April for SMR demonstration projects. So we'll have this invitation for projects on a biannual basis. So twice a year, we will look at and assess any projects that vendors or other interested parties want to site at one of the CNL sites. And this year, we had 4 responses to our invitation for submissions of a project. So we think that that's really exciting and very exciting news for the nuclear industry in general. We've divided our siting project into 4 stages just to allow a bit of a staggered approach in reaching the goal, which is a project execution of building a small reactor demonstration at a CNL site. 3 of the 4 responses that we got fell into our stage 1, which is essentially a pre-qualification type of stage. But 1 proponent was already at a stage 2 type of application. Going through the different stages, we would of course have more detailed information required of proponents, and we would do a more thorough due diligence on our part in looking at the proponents, their technologies, the fit for that technology in Canada, and the fit also in terms of this holistic view of these demonstration reactors with other technologies. Next slide, please. Our hydrogen research is also focused ultimately in cogeneration of hydrogen with the small reactor. But more short term, we're looking at the transport sector. There is a lot of renewed interest in using hydrogen for transport, hydrogen for domestic vehicles, large vehicles, trains. We've done some feasibility studies to look at hydrogen trains in a large urban center in Canada to prove that it is a competitive technology to an electric train or other green options for that kind of commuter train scenario. So we're very excited to see this sort of movement. It allows us to focus on hydrogen production with sufficient amount of production to fuel all of these vehicles that we hope to see on the roads, and also the safety aspects of hydrogen. If ultimately we would like to couple a small modular reactor with hydrogen production in sort of a remote community or an industrial off-grid site, it's really important that we understand the safety aspects of that hydrogen production and that all of the regulations are in place and we have all of those safety questions answered before we look at that holistic solution. As well, we're starting to look at questions like how would you license a small modular reactor and a hydrogen production plant together. So these are questions that we can start to look at now and provide those responses and data to support government regulation and decision making. Next slide, please. And I'll just end my presentation with this concept of a clean energy research park. So we're looking now at establishing a clean energy research park at the Chalk River Laboratories. So we're in the early stages of this concept, but really what it is to provide a venue by which people can test their clean energy technologies alongside the nuclear research that we're doing. So we want to be able to host technologies that want to demonstrate affordable, reliable, low carbon energy systems holistically to show that really it is this connection of all of these renewable technologies and nuclear that will create the energy needs that we need for the future domestically and also internationally. And I think that is my last slide. So I will turn the last slide over to Sherry.
Thank you. I'm going to go back to where Shannon kind of started us. She had our 3 points, and one of the points she made is that nuclear power plants can be coordinated with renewable generation to help maximize our need for a clean energy future. And hopefully through the course of today's presentations, that point has been well illustrated. We started with that flexible operations as a need. It's a growing need right now for existing plants. But if you look at the overheads, we're also looking at how we are using everything we're learning from flexible operations so the next generation of plants also has that ability right from the start to be flexible and even more flexible. We need to consider going forward other things to also increase the flexibility of the plants, ensure the grid resiliency. We talked about some of the critical grid services, and also how we can focus to maximize the economics of the plants as well. We talked about the integration with the energy systems to produce a usable product and the economics with those. Those studies are underway from an industry standpoint. There's a lot of interest around those. And there is a lot of interest that we also continue to look at other things that help support the plants long term, like the robust fuels, the enhancements to the design of the plant, even into the future, maybe some thermal storage, thermal bypass options, and then of course the hybrid energy systems. So innovation and advances in technology are needed, and they're happening right now. I think with that, we're ready for questions.
Wonderful. Thank you so much, Sherry, and thank you to each of our panelists for those outstanding presentations. As we shift to the question and answer session, I just want to remind our attendees to please submit the questions using the question pane. We only have a few minutes left of the webinar, so I encourage everyone to still submit their questions, and any questions we do not have time to get to, we'll connect with those attendees offline after the webinar. Our first question today, I'm going to direct it to one of our experts, but any of the experts, please feel free to jump in and add anything you want to the question. Our first question is for Shannon. Shannon, are integrated energy system options applicable to both existing fleet reactors and to advanced reactors? And was one of these options a better fit than others?
Thank you, Katie. Yes, absolutely. These options are being considered both for existing fleet and advanced reactors. They have different challenges associated with both. When we think about existing fleet reactors, the easy option is looking at electrical integration, such as the study we're doing with reverse osmosis, that requires the fewest regulatory changes and reviews associated with that. However, that does not negate the fact that we're also looking at thermal integration. Those are larger challenges associated with retrofit of an existing facility to thermally integrate with other processes such as hydrogen production, as we have discussed. However, it's something that is possible, and these regulatory challenges are not something that can't be overcome, and we're working through that right now. With regard to advanced reactors, these integrated energy system options can be built in from the beginning with the design of these systems and review and licensing of the systems. And advanced reactors often offer higher temperature operation that may provide more efficient connection with some of these other applications. But there are techniques that we can apply for lower temperature light water reactors in order to boost the heat coming from those, such that we still can achieve integration with some of the higher temperature applications, albeit perhaps at a slightly lower efficiency.
Wonderful. Thank you so much, Shannon. Our next question is for Mark. Mark, our attendee wanted to know, in this integrated system, renewable energy taken with or without subsidies?
Thank you. That's a great question. There are a lot of assumptions that are made within the analyses that we performed, and I invite anybody interested in those assumptions to take a look at the 3 reports that are cited on the slides that I provided. Our rule of thumb was that there are absolutely no subsidies included for renewable energy, for nuclear energy, for investment, or for production in any way, shape, or form. So in other words, we had everything competing on a technology and cost-only basis. Now, that said, there are obviously assumptions around what the technology costs and efficiencies are that are included, and we perform sensitivities around a number of those to be able to allow us to be able to think about a range, not just our projection, but then a range around those projections.
Great, thank you, Mark. I think we have time to maybe squeeze in 1 or 2 more questions. Sherry, our next question was for you. In the Midwest and Northwest regions, is cycling on a daily basis or more of a seasonal thing?
That's good. It's definitely in the upper Northwest, it's seasonal, spring and fall, based on the hydro flow. In the upper Midwest, it's an interesting case study. It started off primarily as a seasonal. Again, the spring and fall being kind of those shoulder months, but now we're starting to see that it's moving into the summer as well. The need to be flexible.
Wonderful, and we're having tons of questions coming in from the audience. Again, if we don't have a chance to answer those, we'll definitely connect afterwards. Our final question I'm opening to the panel is, why prioritizing hydrogen over battery storage of electricity? Does anyone want to comment to that?
So in terms of the analysis that we performed at NREL, we prioritized industrial processes, looking especially at an alternative product, for example, hydrogen or desalinated water or the liquid fuel or even a thermal product as part of our analysis. We have extensive other work going on in other projects that are looking at electricity storage, whether that's battery storage or flow batteries or compressed air energy storage or even pumped hydro. There's a lot of different electricity storage options that we have other analyses using similar techniques and somewhat comparable work between them. I think that the opportunity then is to have a discussion about which is a higher priority based on the results of all these analyses.
Wonderful. Does anyone else want to comment to that? Okay, great. And with that, I'm sorry to say we're out of time since we had such wonderful presentations. Again, thank you. I want to extend a huge thank you to all our expert panelists and to our attendees for participating in today's webinar. Again, as we said, for all the great questions we didn't get to, we'll connect with those people after the webinar. We very much appreciate your time and hope in return there's some valuable insights that you can take back to your ministries, departments, or organizations. Please enjoy the rest of your day, and we hope to see you again at future NICE events. This concludes our webinar.